In this video tutorial, I'll be focusing on the application of Kirchhoff's rules in determining individual currents in a circuit that cannot be analyzed by the simple series parallel combination method. There are two rules. The first is what we call the Junction rule, which is based on conservation of charge. It states that the algebraic sum of the currents into any junction must be equal to 0. And the other rule is what we call the loop rule, which is based on conservation of energy and the conservative nature of electrostatic fields. It states that the algebraic sum of potential differences around any loop must be equal to 0. This is what we mean by the junction rule. Supposing this is a point in the circuit where the current enters into, or if a current moves away from that point. So supposing there is a current I sub 1 that is, or whose direction is into that junction, all right? And there's another current I sub 2 also going into that point, all right? So according to the junction rule, uh, the sum of the current that is entering, all right, a junction must be equal to the sum of the current that is leaving that junction. So that can also mean that I sub 1 when added to I sub 2 will just be equal to another current that can be denoted probably by I sub 3, which actually is the sum of I sub 1 and I sub 2. Alright, now for the loop rule, here is a circuit diagram that represents, alright, uh, this is considered one loop, alright, so imagine that this is a rectangle, right? The bigger rectangle, represents a particular loop. Then again, there are two other smaller loops that we can imagine here. All right, this one is a small rectangular loop. And then there's another loop to the right. So according to the loop rule, if you're going to travel around this loop, say for example, around the bigger rectangle, and we'll go counterclockwise, starting from, for example, if we start at the terminal of the battery, okay, so as we travel uh, around this loop, the bigger loop, it simply says that the total amount of the voltages, all right, the total amount of voltages, also known as EMFs, must be equal to 0. Okay, we can do that also for the smaller loop. If we go around that small loop, all right, the total amount of the voltages or EMFs must also be equal to 0. So that is exactly what we mean by Kirchhoff's rules. Let me clarify what I mean by traveling around the loop. The word travel is just simply the direction that we are going to imagine if we go around the loop, all right? And that choice for the direction of our travel, by the way, is to be assumed. So you have to assume how you're going to go around the loop, whether it is clockwise or counterclockwise, all right? Such direction of travel around the loop does not necessarily indicate the direction of the current, all right? It may be in the same direction of the current or not. Now, there are sign conventions that we need to follow or obey. For determining the sign of the EMFs or voltages, here is the rule or the agreement. Supposing this is the battery, okay, which has a negative terminal as well as a positive terminal. All right. We know that the shorter vertical line here, all right, or the shorter bar represents the negative terminal of the battery, while the longer one represents the positive terminal. So, if in going around the loop and we pass by this terminal of a given battery, if your direction is from the negative terminal, all right, to the positive terminal, then you have to assign a positive sign for your EMF or for the voltage of that battery. All right, again, traveling from negative to positive will mean a positive EMF for the battery. Otherwise, if your travel is from positive to the negative terminal, all right, if the direction of your travel is from positive to the negative terminal, then you must assign a negative direction for your EMF. Likewise, you also have the sign conventions for resistors. Now, supposing this is the symbol for a given resistor, and that in your travel around the loop, okay, is such that you move in the direction opposite to the direction of the assumed current. All right, as represented here, if the current is to the left, but your travel direction is to the right, so that means opposite. All right, you have to treat the IR product, okay, the IR product, which is the voltage drop, to be positive. Again, if the direction of your travel is opposite to the assumed direction of the current, then you have to assign the IR product, which is the voltage drop, as positive. But if your direction of travel is in the same direction as the assumed current, then the IR product or the voltage must be negative. This is the sample problem. In the circuit shown, a 12-volt power supply with unknown internal resistance, small r, is connected to a rundown rechargeable battery with unknown EMF, denoted here by the Greek letter epsilon, and internal resistance 1 ohm, and to an indicator light bulb of resistance 3 ohms carrying a current of 2 amperes. The current through the rundown battery is 1 ampere in the direction shown. Find the unknown current I, the internal resistance small r, and the EMF epsilon. So in the diagram, as you can see, we have here two um, batteries. The first one has a given voltage or EMF of 12 volts with an unknown internal resistance small r. There is an unknown current, okay, indicated here by letter I, and the direction is uh, from the negative terminal to the positive terminal of this battery or power supply. Now, there is, as described in the problem, a rundown battery with a given internal resistance of 1 ohm, but an unknown EMF or epsilon. There's a current passing through this rundown battery, and the direction of the current is as indicated here. And this, in turn, is connected to a light bulb, an indicator light bulb, with a resistance of 3 ohms, and there is a current passing through it, current of 2 amperes. Okay. Notice also that in the diagram, we have what we call junction point. junction point A as well as junction point B. And you will notice that the way we are going to move around the loop, or the way we are going to travel around the loop, is already assumed to be, for example, around this small loop on the right side. Okay, the travel is in a clockwise direction. For the other loop, the smaller loop on the left, again, the travel is also clockwise. And if there is still a need to use the bigger loop, all right, this is a bigger loop. Again, the assumption of the travel is clockwise. Normally, in other problems on the application of Kirchhoff's, if the currents to be determined are unknown, okay, you have to assume each of the unknown current, okay, as to the direction that they are going to be directed through any given resistor. But here, the unknown current is already assumed to be moving from the negative terminal to the positive terminal of the 12-volt battery. Okay, so that's already given. We have to consider such given direction of the unknown current. Okay, and the solution will now be shown in the next slide. Alright, so the first thing that we're going to do is to consider uh, the rightmost loop, this particular loop, wherein our assumption as we go through the loop is to travel in a clockwise direction. Okay, as indicated here by the curved blue arrow, we will be moving around this loop in a clockwise manner. Alright, so that is the first step. Consider a clockwise travel around the small right loop. Alright, so which part of the loop are we supposed to start from? Okay, so we will start by considering the EMF of the battery. Alright, as you travel clockwise and passes through this battery, okay, you will be traveling in such a way that you will traverse the terminal of the battery from the negative to the positive terminal. So according to our loop rule, if your direction of travel is such that you will be traversing the battery from the negative to the positive terminal, then you have to consider that EMF of 12 volts to be positive. So we write it here, 12 volts. As you continue with your travel, you're going to pass by or pass through this internal resistance of the battery, okay, denoted by small r. Now, the unknown current that is assumed, all right, is shown by this arrow. And since the direction of your travel, okay, is the same as the direction of the assumed current in passing through a resistor, the sign of that IR product, which actually is just the voltage, will be negative. So we put here minus I times small r. Okay, the direction of your travel is in the same direction as the assumed current that we have here. Now, As you complete the whole loop, you will be passing by the next resistor, the internal resistance equal to 1 ohm of the rundown battery. And you will notice that the direction of the current that passes through this resistor is upward. Alright? And that means you will be traveling in the same direction as that current of 1 amperes. So, again, if you multiply 1 ohm times 1 ampere, that's exactly equal to 1 volt. And the sign of that voltage drop or EMF is equal to negative 1 volt, okay, minus 1 volt. And finally, as you cross or traverse, okay, the terminal of this rundown battery, you will be traversing from the negative terminal to the positive terminal. Therefore, the sign of the EMF for this rundown battery must be positive. Okay, so we have included all the IR product as well as the EMFs, because if we now complete the travel, okay, we will go back to this EMF of 12 volts, which we already have listed down in our first equation. So, this is now, the next step now is for you to simplify the equation. 12 volts minus 1 volt, of course, will give you 11 volts. Okay, for simplicity, okay, we can just ignore the sign, the unit volt. So just call it 11, understood to be 11 volts. Bring down the negative IR or minus IR plus the unknown EMF or epsilon equated to 0. So this is our first equation, okay, which we came up with when we consider a clockwise travel around the small loop to the right. So what's the second step? Second step is to choose another loop, okay, the one on the left. All right. So just like in the first loop, the second loop has also an assumed direction of travel that is clockwise. Okay, clockwise. And we will be moving starting from uh, the unknown EMF or epsilon, since you're going to traverse this battery from positive to negative. Therefore, the sign for the epsilon is negative. And then we pass through the resistor having a resistance of 1 ohm. We will be traveling opposite to the direction of the current 1 ampere. Alright? And that 1 ampere, when multiplied to 1 ohm, actually becomes 1 volt here. But the sign of that 1 volt, of course, is positive because, okay, our direction of travel is opposite to the direction of that given current. Now, as we continue here, we will again be moving in the same direction as the given current of 2 amperes. Alright? And the resistance for this, this is a light bulb whose resistance is given 3 ohms and whose current through it is also given 2 amperes. Therefore, the product or the voltage, okay, across this resistor is 6 volts. But since our direction of travel is in the same direction as that current, then we have a negative 6 volts. So that completes our equation using this loop. Okay, simplifying this equation, we will get for epsilon or EMF, if we transpose, for example, 1 volt minus 6 volts is supposed to be negative 5 volts. All right, negative 5 volts will then be the value for our unknown EMF or epsilon. Okay, now what does a negative EMF suggest? Okay, this is negative 5 volts. It simply suggests that the actual polarity, of our battery should have been such that uh, the positive terminal is supposed to be on this side of the battery. In other words, this polarity of the battery, as shown in the diagram, supposed to be reversed. Okay, the actual polarity of the battery should be the reversed polarity, as indicated by this negative 5 volts. But right now, we will just leave it as is. All right. Our unknown EMF has been determined to be negative 5 volts. So, uh, that is one of the unknown variables that we are looking for. Okay, the EMF of the rundown battery. We still have two unknown variables, the small r as well as the current I. So, originally we have three unknown variables, but now we have already a value for the EMF, which is negative 5. So, the next thing that we're going to do for our third step is to use the junction rule. All right, the junction rule is to be applied at one of the junctions or junction points, which is point A. Here is point A in the diagram, right? If you notice, if you're going to trace the flow of the 2 ampere current, okay, this particular current, 2 amperes, when it passes through point A, it's actually entering that junction. Okay, this 2 ampere current, we say, is directed into the junction point A. All right. Now, the given current that passes through this rundown battery is also directed into the junction point A. All right. So, 2 amperes and the 1 ampere current are both directed into the junction of point A. Okay. But the other current, the unknown current denoted by capital I, if you're going to trace it back, it actually is leaving or moving away from junction point A. So we can establish, okay, the relationship among these three currents. Okay, according to the junction rule, the currents that's entering a particular junction is equal to the current or currents that is leaving that particular junction. So our equation will be the unknown current I is just equal to the sum of 2 ampere current and the 1 ampere current, which obviously is equal to 3 amperes. In short, using our junction rule at point A, we're able to determine the value of the unknown current I, and this is equal to 3 amperes. So that's the value of the current that we are looking for, denoted by capital I. All right, so far we already know the EMF of the rundown battery and also the value of the unknown current that passes through the 12-volt battery. So the last variable that we are going to determine is the internal resistance, small r, of the 12-volt battery. How are you going to do that? So the next step, of course, is to solve for the value of r. We simply, all right, we simply make use of the fact that in our equation, first step equation here, the one that's simplified, we say that 11 minus IR plus the EMF is equal to 0. Since we already know the value of the current I as well as the value of the EMF or epsilon, therefore we can determine the value of the small r or the internal resistance by simply substituting, okay, those already determined values for epsilon as well as for the current I. That is 11 minus 3r minus 5 is equal to 0. Okay, 3 is our value for the current, okay, 3 amperes, to be multiplied by the internal resistance R minus, okay, epsilon, which is the value for the EMF, the unknown EMF, which we already got to be equal to negative 5 volts. So, simplifying, for us to solve for small r, we will get this value for the internal resistance. R is equal to 2 ohms. See, we are done in determining the unknown variables. Okay, the value of the EMF of the rundown battery, okay, the current I in the 12-volt battery, and the internal resistance, small r, of the 12-volt battery. The next step is for us to show how we are going to check, all right, how we are going to check if our equation, the first equation that we established earlier here, okay, we will prove that indeed if you're going to add the EMFs around this loop, all right, the right side loop that we chose, we will prove that the sum of the EMFs and the voltages or IR products will indeed be equal to 0. And we will do the same for the second equation that we have here. We will also prove that for this second equation, the sum of the EMFs around this second loop that we choose, okay, the sum of the EMFs plus the voltages or voltage drops must also be equal to 0, and that is coming in the next and last slide. In our checking, we just simply substitute our computed values in our equations that we have established earlier. All right. So for the first, or for the right loop, we already obtained this equation earlier. 12 volts minus IR minus 1 volt plus the EMF equals 0. So when we substitute the values for the current, the value for the resistance R, and the value for epsilon, this is what we get. Okay, 12 minus 3 times 2 minus 1 minus 5. Is this equal to 0? Yes, it is. So we say that our equation 1, based from using the right loop, is indeed correct. Now, for the second loop, okay, the one on the left, we also establish the equation earlier as negative epsilon plus 1 volt minus 6 volt equals 0. Okay. The value for the EMF that we got earlier was negative 5. But when substituted here, that becomes negative of negative 5 plus 1 volt, alright, minus 6 volts. So we still get 6 minus 6 or equals 0. Again, our equation in number 2 based on the second loop is also correct. Okay, to further convince you that our answers are indeed correct when you use the two loops, the two smaller loops, okay, we can also check them, this time by choosing the bigger loop, this one here, alright? This is what we call the bigger or the big loop. We just go around also in clockwise direction, starting from starting from the 12 volt EMF. Okay, this is how it goes. Okay, so negative to positive, you go around in clockwise manner, that means 12 volts. As you pass this small r and in the direction of the unknown current, that means our sign for that IR product is negative 3 times 2 volts, and you go all the way passing through the 3 ohm resistor of the light bulb whose current is 2 amperes. And since you go in the direction of the current, that means you have minus 6 volts. And simplifying, we get 12 volts minus 3 times 2 is 6 minus 6, and this gives us also equal to 0. So that is our final checking. This is all for today, and hope to see you in our next video tutorial.